Hello, it is my pleasure to welcome Risto Miikkulainen. He is a professor of computer science at the University of Texas at Austin and associate VP at Cognizant AI Labs. His current research focuses on methods and applications of neural evolution, as well as neural network models of natural language processing and vision. He is the author of over 450 articles in these research areas. At Cognizant, and previously as CTO of Sentient Technologies, he is scaling up these approaches to real-world problems. Risto is an IEEE Fellow. His work on neural evolution has recently been recognized with the IEEE CIS Evolutionary Computation Pioneer Award, the Gabor Award of the International Neural Network Society, and Outstanding Paper of the Decade Award of the International Society for Artificial Life. Welcome, Risto.
Thank you, Kevin. Yeah, so I will talk about some work that we've been doing at the Cognizant AI Labs here in San Francisco. This is the team that's worked on it. It's in general a way of supporting decision-making, and it has many applications in all over the different areas: healthcare, engineering, design, education, many other marketing, perhaps business. But here today, I mostly want to give you an intro of what it's like, what the technology is like, and then give an overview, a tour of a special application that we developed over the last year and a half on optimizing COVID-19 interventions. So the big picture, the big question is, how do we make good decisions? Anywhere in life, but also in business and in government and many other areas. Like here, there are organizations that now have data about their customers, about their patients, about their students. They know what they will do in different situations. But that's not yet enough to decide what you should do, how you should manage their expectations and how you should interact with them. So the decision-making is a different problem from prediction. And it's a difficult problem. Because even though in prediction you often have goals or prediction, the targets available, you know what actually happened over time. In decision making, you generally don't know what the optimal decisions are, and you also don't know all the variables that go into making those decisions and affect the outcomes. You have many factors that actually interact non-linearly, and therefore methods that have been well used in industry for a long time, like linear programming, gradient descent, they are not very effective as a decision-making optimization tools. So instead, we need to bring in a different kind of technology, and that is search. Of course, there's many different search methods, but the idea generally is that search allows you to find solutions you don't already know. You just have to do it efficiently enough so that you can solve real-world problems. And that's the challenge that we are facing. That's what we are trying to bring to market. More efficient search methods that would allow you to support decisions. Now, in general, deciding what decision strategies to employ, you need to evaluate them when you're doing search. You could do it in the real world, like you have a candidate, this is my strategy, let's see how well it works. But that can be very costly in the real world. It can also be costly even if you have a simulation of the domain that you have, for instance, in some kind of medical domain or in some kind of engineering design domain. It can be computationally costly. It's very difficult to build such simulators. So instead, what we need to use is data. We need an approach that uses two models, not just one. There's one model that's based on decision-making, based on historical data, on contexts and actions and outcomes. That is, given history of this is what people decided to do in the past in these situations, this is what the outcome was. That's historical data, and you can collect that, and that's exactly what organizations have already. And when you have that kind of data, you can build a predictive model. That's a standard machine learning approach, stochastic gradient descent. It could be random forests, something that, given a historical data set, can learn to model it and learn to predict. And once you have that, you can use it as a surrogate for the real world. And that means that you can then use the surrogate to search for good decision strategies. This other model, the prescriptive model, that goes from context, which is a problem definition, directly to actions, which is how you want to deal with the situation. And when you are searching for a good decision strategy, you're searching for this model from context to actions such that your outcomes are maximized or optimized. Typically, there are a couple of objectives. There's something that's a performance objective and something else that's a cost objective. And you have to find something that optimizes both of those. And this is why you need to search, because we don't know what the optimal strategies are. So let's try to find them through search. Now, the mechanism for doing this search that we picked or we used is evolutionary optimization or population-based search. And that turns out to be very powerful in this kind of situation in particular, where you need to evolve a neural network as a model that maps the context to actions. All right, so we didn't come here by accident or even necessarily by a big design. We came through several applications that we built over the years that had pieces of these already, pieces of this triangle. So for instance, in a project called CyberAct, which was a collaboration with MIT Media Lab, we provided the optimization engine for cyber agriculture, that is computer-controlled growth environments. This guy here, Caleb Harper, built those environments. Everything is computer-controlled. How much light there is, what light wavelengths, how long the light is on, also water, nutrients, temperature, all of those are computer-controlled. And it turns out we don't know how to do it. If you can control everything in a growth environment, what is an optimal growth environment? Biologists don't really know. And therefore, we brought in the evolutionary optimization piece in order to find good growth recipes. And we were working with basil. So the goal was to make large basil plants as well as very tasty basil plants, have a lot of spice and kick in the plant. We initially started with 200 recipes that were hand designed. Some of those were known to be good, and others were just exploratory, a little different, covering as much of the space as possible. And then we trained this predictive model, the surrogate model, to go from each of these recipes to the outcomes, the size of the plant and the taste profile of the plant. And once we had this surrogate model that could predict the outcome, we could then search for the recipes. And this was really just a single recipe. There was no mapping from anything, but it was a search for the profiles of light. And it was fascinating that in this process, we actually tried over 1 million different recipes against the surrogate, not by planting them. It takes 3 weeks to grow basil, but by just testing, asking the surrogate how good this recipe is. And in this process, evolution discovered something really surprising. And that was that basil does not need to sleep. Basil is happiest if it sees 24 hours of sunlight, or actually in this case, artificial light, and then it thrives. It grows big, it grows tasty. And this was a big surprise to the biologists in the team. They thought that in nature there's daylight and nighttime, and we should turn off the lights for at least 6 hours. Well, evolution quickly discovered that it would have all the recipes up to that boundary of 6 hours. So we opened it up and discovered that 24 hours of light works really well. This is a great example of how this kind of a search mechanism can find something you don't already know. That's something that's even actually surprising, and you bet that it wouldn't work, but it does if you let evolution to do its job. It does not have the human biases, and therefore it can find surprising things. So that was one part of it, using a surrogate, but discovering these recipes directly. Another part was this mapping from context to actions. And we first tried it in this other domain here on the right. This was a domain where we were designing web interfaces. So colors, text, the organization of the page, that's now controlled by an evolutionary method, a neural network that maps what we know about the user that comes to the site and what kind of design we give this user. And then we measured how often these users would convert. They would click on that button, find my program. And it was very interesting in that, again, evolution was coming up with designs that were very, very different from what the humans had designed. I mean, there was already a website, and they already had humans who call themselves conversion scientists, optimized the design so that as many people would convert as possible. But it turned out that our design, so evolutionary design, was quite different. They used Gary's colors, like neon and this kind of purple, pinkish color, and also very active, strong statements, find my program, choose a program, and so on. To the extent that the human designers, when they were watching evolution, trying to discover good designs, they called it the ugly widget generator. Because to them, some of these designs look ugly, but they performed better than their own designs, 45% better in this case. And in general, the range is pretty broad, but routinely we can exceed what humans can come up with. And here the interesting bit that we learned was that it was really useful to map the user to his or her own design. We know something about users. We know their location, we know the time of day there, we might know the weather, we know what operating system they're using, or whether they're on a phone or computer and so on. So we have some information, and it turns out that that was already enough to decide to some degree what kind of designs they should get. So now putting these two results together, the power of surrogate modeling and the power of customization of these interfaces, we come up with this triangle that then is our approach to decision making. And it's called Evolutionary Surrogate-Assisted Prescription. And this is how you deploy it in the world. You start with those context, action, outcome data that you already may have collected. You use it to train a predictor model. And then with the predictor, you can evolve the prescriptor, the decision policy. Once you've done that, you can deploy it in the world. And when you do it, you get some more outcomes, and you can augment your data set and actually gradually improve your performance over multiple iterations. And even if you had the whole data set in the beginning, it might still be good to go through this loop every now and then. The weather changes, the seasons change, the fashion changes. So the world always changes, and therefore refreshing your models is always a good idea. So let's dive a little bit deeper into what's going on in here. And I'm not sure if people know in general what evolutionary optimization is. So I'm going to give you just an example and kind of an intuitive feel for it. And then we'll look at the example of COVID-19. So in the COVID-19 application, we are evolving the decision maker, whether you should close the schools, close workplaces, shut down public transportation, require masks, all these actions that are non-pharmaceutical interventions. They are designed by the decision maker, which is a neural network that we evolve. We don't know what the optimal decisions are, so we'll try to find it by evolving a neural net for that task. So let's look at how we do that, how we evolve the neural network. So the general idea of evolutionary optimization is that you have a population of solutions, not just a single one that you gradually try to improve like you do in gradient descent or reinforcement learning. No, you have an actual population, hundreds of them. And that means that they can be very different initially. We initialize them randomly sometimes, or just initialize them very broadly, so they're very different. And then you take each one at a time, and you can decode them into an individual. So this is usually the genetic representation is a string, for instance, values of the weights of the neural net, or a tree, like a structure of the neural net. You decode it into neural net itself, you put it in the environment, and you run it. You evaluate how well it performs. And in this case, it might be making these decisions about non-pharmaceutical interventions that keep the cases down and are as light as possible. So that becomes your fitness. And then when you do that fitness evaluation for all of these individuals, you can then decide which ones are your good individuals and which ones are bad. So throw away the bad, keep the good, and then try to do some search. Create new ones that are based on the good individuals. So you take two parents that have already been evaluated to be the best in your population, and some of the best. You might do crossover, like here. You take part of one parent from one part of one parent and another part from another parent and glue them together, and you get offspring. And the idea is that this way, hopefully in your offspring, one of them anyway, you combine the good traits of both parents. So the offspring are better than both parents. And it's okay if that doesn't always happen, because you just do this over and over and over again. So if you occasionally find some really good individuals this way, you're making good progress. And that's the idea of evolutionary search. It's not just random search, not at all. You are focusing search on a good individuals, and then you are exchanging genetic material, recombining those individuals so that you find something even better. And you always have mutation as well, so you can change some of these individual components of the offspring so that you can find things that parents don't already have. So that's the basic idea of evolutionary search. You create variation, and upon that you have selection, just like you have in biology. That's how much biology there is. Mostly it's all computational. Now, I also like to illustrate what it really looks like, or how it might really happen. I like to think of my population as something that I have in a table in front of me. That's my whole search space. These are all the possible strategies for assigning MPIs, or all the possible growth recipes or web designs. They are each one is a separate, different point on this plane. Once I create my initial population, that means I spread it very broadly, and I evaluate each one. So I get some dots that are larger than others because they perform better than others. So we can already see that there's some areas of the search space that are not so good, and then other areas that are a little better. And I select the parents from those areas that are better. These are some of the best parents. And then I form offspring by combining elements, part of the neural network from one parent and the other part from another. And then I do this for many times. I throw away the bad ones, replace them with these offspring of the good parents. And here already in generation 2, you can see that it's no longer quite so broad. The dots are larger. We're getting better solutions that are more focused in areas that work better. And over several generations, you'll end up with a population that's mostly focused in areas where good solutions are. Now, there's never really a guarantee that you find an optimal solution. These domains are nonlinear. You can never really guarantee that just mathematically, but there's a high likelihood that you find several that are good. And it's also the basic idea of evolution is that you got to keep your population diverse. So you don't want to focus it too much. You want to have some alternatives because they can serve as stepping stones. You might combine this one and find a really good one over here where you don't have currently anybody. So you want to have diversity, but in the end, you do have a collection of individuals that also include some really good ones. That's the basic idea of evolutionary search. Now, how well does this work? Now we're back to ESP now, and I want to illustrate how the different elements of prediction and prescription, those two models actually interact. So in a very simple task, we have a context that's one number and an action that's one number. So given that we are at state or context 8, then the best possible action is -1. And we can see what the actual ground truth is. This sine wave specifies the best possible action for any possible state. And so that's what we try to find. We try to find a sine wave, a prescriptor that actually replicates that sine wave. And here we have an illustration of how this learning progresses. In the background here, we actually have not the ground truth, but the current predictor, a neural network that tries to learn what the world is like. And it learns it by observing these samples that we take from the world, these dots. So after seeing 25 samples, these dots, so the context and action and the associated value, we train a predictor, and that's what it looks like, this color coding in the back. It's not quite sine wave yet after 25 samples. There's this area, for instance, it's completely lost. It shouldn't be there. It's mostly in the middle because it matches a lot of the ground truth, but there's still quite a bit to be learned. This is, of course, the actual ground truth, and this is what we currently learn. Our prescriptor would return values along this orange line. And it's actually quite remarkable that during learning, the prescriptor is actually better in prescribing good actions than you would expect given the current state of the predictor. That would be the white line. That's what you should do if the predictor was really the ground truth. But it turns out it isn't, and our prescriptor has learned a better function than the predictor would allow. That's really surprising, but it has to do with learning over time, seeing many different predictors, and learning on average. It's like ensembling effect. And in general, we get really good rapid learning this way. After 25 episodes, we're already quite close to the middle, and then the sine wave starts to emerge after maybe 100 epochs or so, or 100 episodes of that means these dots, these samples of training and testing the prescriptor. And compared to direct evolution or reinforcement learning like PPO, it's much, much better. This is after 1,000 episodes, the PPO is starting to get some of that sine wave, but it's nowhere near as accurate as ESP is. So this is a comparison in a reinforcement learning kind of domain, function approximation, to demonstrate that the predictor and prescriptor learn together to perform well in this task of finding optimal decision policies. Okay, so now that's a good starting point. That's a scientific point, a quantitative evaluation. But what if we want to take it to the real world? We have customers, we have decision makers. They face design choices, marketing choices, healthcare choices. How do we make it so that they can trust the system and actually deploy it and take advantage of it? So there are a couple of different dimensions that we've addressed, three actually. So the first one is that the users have to be able to manipulate the decisions. They get a recommendation for action from the AI model, from the neural net, but now they need to be able to modify it. They have maybe an idea that this looks a little too much like that. I would like to change it this way. How good would that be? And indeed, once the prescriptor is done subscribing or recommending something, the user can edit that recommendation and ask the predictor to evaluate how well would this modification work. And this way, the user can convince him or herself that the solution, eventually the prescription, is good, that you can't find anything better by hand, starting from the AI's prescription. So that's a really good tool to have. Another important aspect is that we need to know whether we can trust those predictions. If we have a recommendation to make this action, and the prediction is that it will, make $5 million, what's the range of confidence? Is it going to be plus minus $50 or plus minus $500,000? That's a big difference on whether we should take that action. And we developed some technology, a system called Rio, which fits a Gaussian process model to the residuals of the predictor. And therefore, it gives us the confidence bounds. And this way, the decision maker gets to see how confident the system is about its recommendations, or the recommendations of the decision maker, him or herself, if they want to make the modifications. And also, we have recently built and tested a version of the prescriptor that's actually not a neural net, but it's a rule-based system. So it's a collection of rules. So when it makes its recommendation, you can read why. You can read the rules, you can see what it's looking at in the data and why it's making the decision. Sometimes they are understandable, other times they may be a little bit obscure, but it is a big step towards explainable AI in this context of ESP. Okay, now let's get into the COVID-19 application. This is, like I said, a work that we started when the COVID pandemic started. In May, we had our first models built, and we've since then been running it every night and promoting new versions on the web. We have a demo on the web that everybody can access several times a week. And it's very interesting to see how the pandemic has changed over a year and a half, and also our models have changed for a year and a half. Now, it is an application of ESP, so there's a predictor and prescriptor, and both are learned. Now, I need to emphasize something here. By now, we all used to looking at these plots like this. How does the COVID-19 cases, deaths, hospitalizations progress over time in different countries and regions in the world? And also, we've seen, in some cases, people build models that predict what will happen in the future. And maybe they also have these confidence bounds around the prediction. So this was, for instance, middle of last summer. I think this is US, it might be UK. And the prediction was that the current state of the restrictions, the cases would stay relatively constant for quite a while. Indeed, some of these prediction models don't just look at the curve, They may be based on epidemiological modeling, 100-year-old technology, and they may even take into account the non-pharmaceutical interventions, NPIs, in order to make those predictions. But what we are bringing here to the table is something new. We are not just predicting, we are also prescribing. So it's not just that we're asking what will happen, but we're also asking what could we do about it? How could we make this curve sink and stay low? So this is the novel aspect, and ESP provides this prescriptor that allows us to assign these NPIs. And indeed, we're learning both the prediction and prescription at the same time, adapting to different stages in the pandemic. If you're interested, there's a very detailed scientific paper about this approach written late last year, and well, early this year actually. Now, but let's go over what the model is like, and then we'll look at the demo. So the first step is, again, to build the predictor. And initially, we were thinking of building just a standard compartmental model, SEIR model, standard epidemiological model, maybe add a network model on top of that, or agent-based modeling. It turned out that it was just computationally not feasible. To have that level of accuracy, we would need to train or fit the model for something like 7 days. We needed to run this daily, or at least several times a week. But at the same time, interesting enough, this is the first pandemic where there's real-time data coming out from all over the world about how the pandemic is progressing. And in particular, this group at Oxford collected data from all around the world, all countries they could get their hands on, people in there, not just of the cases, hospitalization and deaths, but also what restrictions the government was imposing there. They will read in the government communiques, press releases, press news, and everything, and then coding all this data in a common format, so that if schools are closing in China, how does that map to schools closing in Italy, for instance? Multiple different levels. I mean, it cannot be very accurate, but you can at least have a couple of different levels, like completely open, completely shut down, and something in between, different cohorts of lower density, or various mitigations of social distancing and so on. So these are different levels in all those different NPI dimensions. And they came up with a common encoding so we could get the same data in the same format from all around the world. And that actually turned out to be a big insight, that we don't need to really understand epidemiology underlying the pandemic. If we have such time series data about how the pandemic is progressing, all these complex interactions of people, mobility, demographics, obesity, all of these are actually expressed in the data set itself, in the time series itself. And if we have enough data, we can model it and we can predict. And we can do it at least as well, if not better, than the compartmental models. In many cases, better when there are many factors that compartmental models can actually easily take into account. And also, we can have a system that changes continuously every day as the data changes, as the pandemic changes into a different mode or different phase. And that's also very hard to do with compartmental models. So this was a big deal. Initially, we had very little data. In May, we only had 2 months of shutdowns and various restrictions. So it was important to come up with a neural network model that fit the data, but also obeyed some of the basic epidemiological principles. So by separating the sequence of cases from the sequence of NPIs, it was possible to impose constraints like herd immunity, that if you have a really high exponential peak, it will eventually come down. And also, if you have more restrictions, the number of cases should not increase or be worse than when you have less restrictions. So monotonicity constraints like that. And that does help. Learning under such constraints, even with little data, you can do better. But now we're in a different stage. We have so much more data that we don't actually need those constraints. And it's actually better not to have them. We found that the data is a more accurate source than our assumptions about how the pandemic progresses that we would put into epidemiological models. All right, now the second component is the prescriptor. That was the predictor, the surrogate model, and this is now the prescriptor. It receives the same input data sequence as its input. We look at about 21 days into the past. We don't have to look at the whole history from the beginning of the pandemic. It's enough to see where the curve is going now, how it's behaving the last few weeks, because that's what the effect of the MPIs usually is. They come out in a couple of weeks. The effect comes out. And then we are making recommendations for these various different dimensions of MPIs. Schools, workplaces, public events, gatherings, public transport, stay at home, which means lockdown, internal movement, travel. There are also others. There's testing, contact tracing, mask mandates, and a few others. We started with only these 8, and we added more as the pandemic progressed, like masking was a big thing to add. And we could add more, like vaccination levels and so on. They are generally context variables, but we could also have some policies on vaccination here. So this is, again, models change, pandemic changes, and we have to react to it. And we've been able to track it pretty well. So notice, though, there are no gradients here. We don't know what we should do. Nobody is going to tell us that the optimal way to have public events is to have them at 50% capacity. Nobody can tell that. So this is something where we have to use evolutionary search, the mechanism that I described, population-based search. And then each one of these neural networks represents a whole policy. Given data in a particular country, in a particular period of time, it'll make a recommendation. We have to evaluate it over many countries, many time periods, and then see how well they would have resulted in the cases coming down, and also how strong these recommendations are. Because we want to minimize both. We want to minimize the cases. We want to be as lenient as possible, because closing down a whole country is a big economic impact. So we want to avoid that if we can. And that means that the optimization problem, the evolution problem, is multi-objective. We have 2 objectives, and we have to find various ways of trading them off. And that's precisely what happens when you evolve these neural networks. This is actually an animation of the whole population in the evolution while we are learning in the current with the current data set today. This was some other day, months ago. But it shows you that each one of these dots represents one neural network. There's a whole neural network behind it. What we are plotting here is how that neural network fares along the 2 objectives. One of them is the number of cases. The other one is the cost, economic cost, or the stringency of the MPIs. And as you can see, that initially we randomly initialize the networks, so they tend to be here pretty far from the bottom left. But as evolution progresses, it discovers neural networks that simultaneously minimize cases and are as lenient as possible. So you have more solutions that are on this frontier here. It's called the Pareto front. It's the optimal set of trade-offs that you want to get as a result. So if you have 2 objectives, it's a multi-objective problem. You cannot find a single solution that optimizes everything. It depends on your preferences. Do you put more weight on minimizing the cases or minimizing the cost? If you really care about the cost, but not cases, you might want to pick some neural networks here. The cost is very low, even though the caseload is very high. Or if you really, really want to bring down the pandemic number of cases, no matter what the cost is, you would pick one of these neural networks. The number of cases is very low, but the MPI cost is very high. So most decision makers in most parts of the pandemic, initially, of course, there was nothing, cases exploded, and then there was a full shutdown, one of these, and now we are finding ourselves somewhere here trying to balance restrictions with their effect on cases. So that's a general setup. Now let's go and look at the demo. The demo is actually on the web. You can go there yourself and you can explore and interactively try out different things. But I'm going to just shout out and show some interesting phenomena here. This is what the demo looks like. It is starting point is a map because we really have a global model. We are learning from all the countries at once and applying the knowledge to all the other countries. So you can go and pick your country of interest here. Each dot represents one country, or in some cases, like in US, we have the different states. In UK, we have England and Northern Ireland and so on. And we're also expanding to provinces in Brazil and India and so on. This is still very coarse. So we are assuming the data that Oxford puts together is assuming that the whole country is represented by one set of MPIs, which is not quite true, but it's a first approximation. So we can now pick one of the countries. If it's one of the darker ovals, then that means that we calculated the uncertainty for it. It's quite computationally expensive. We don't do it all the time, but we do it for the bigger countries and those that have the most cases. So now we picked India, which is of course interesting because there was a huge peak and then it went away. And this is the history of NPIs. This is cases. We could model other things too, but we're modeling number of cases over time, new cases per day, smooth average over 1 week. And then here we have the restrictions, schools, workplaces, public events, and so on. One is represented by one row. And then the color coding tells you how stringent they are. So lighter is more lenient, dark means shut it down. And as you can see, still India is relatively strong in terms of their restrictions. And it turns out that we can go actually and release some of these, even all the way to something like this, I think. Oh yeah, right. So here is a prescriptor trade-off. So remember I showed you that Pareto front trade-offs. We take the Pareto front and we linearize it here so we can pick those prescriptors that minimize cases no matter what the cost, and those that minimize MPIs no matter how many cases we have. So we can move from more stringent to more lenient MPIs, and as a result, you see that the predicted number of cases goes up and down. So here, this is actually quite a bit more lenient than what's currently happening in India, suggesting that they are actually in pretty good shape, knock on wood. Even if we open up, the cases will go up maybe, but not so much. However, notice what the uncertainty is. This is a precarious situation. Opening up the economy too much could cause a large explosion in cases, even bigger than they saw before. That's what our uncertainty tells us. If you go even further, then the prediction is that it will most likely cause an explosion, and it could be much worse than what we saw before. So now this is only schools and stay at home. So some relatively mild lockdown would cause you trouble. So that's the basic function here. You pick a country, you pick a prescriptor, and you can look at what the predictions are. But we've also built some interesting functionality to make this more interactive and to make it more interesting. So let's go someplace else just for fun. Let's go to Iran, for instance. In Iran had a very more recent peak, and it's still here, now coming down a little bit. So this is an interesting situation. Are we over the hump or are we not? Now, so if you go to the same prescriptor number 13, which is relatively lenient, it suggests that it's actually pretty good. The cases are coming down, but there are some aspects here that the decision makers might want to consider changing. So workplaces, recommendation is that the workplaces should be closed. You shouldn't go to work. And also public events should be canceled. There's pretty stringent stay at home. But a lot of other things are open. So now we have an interface where you can edit those recommendations by hand. So here you go to the AI's recommendations, and you can make the workplace closing more lenient. This is really the most lenient level 1, that you do have to exercise some caution. And now we can go and change it, trade it off with something else. We might have public information campaigns, testing policy, contact tracing, and masks, and hopefully can trade off. And if we do all this, can we open the workplaces to at least to level 1? And indeed, then that's what our models will tell us. It will evaluate that recommendation. It's this yellow dotted line here. It shows that it's a little worse, but not much. So it's actually relatively safe to do. And this is some useful information to the decision makers. And as a matter of fact, we actually talked with, not with Iran, but Iceland, where we actually had the models shown to the cabinet level people, decision makers, prime minister and health minister, and when they were planning on opening the schools. And we did this kind of custom editing of the various levels of school opening, and made a recommendation that you cannot open the schools up completely. There needs to be kind of a medium level restriction. And they did pretty well when they opened up, and the pandemic is going down quite well there. So this is one case where this scratchpad actually really works. It allows the decision maker to look at alternatives and make a decision. Okay, there's one more functionality that we just implemented about 2 weeks ago. Let's say we could go to the US and take a look what's happening here. So this is the functionality of counterfactuals. So we can go back in time and see what could have happened if we had different kinds of MPIs. So let's go to July 1st and apply, and we'll see what was happening then and what alternatives we had. And it actually turns out that we were in really good shape in early July in the US. Vaccination rates were already pretty high. A Delta variant wasn't there. And even if we almost completely opened the economy, just have some caution in workplaces, the prediction was that we'd be over. The pandemic would be over. This is where all the fall plans came. And then came the Delta variant. And you can see that it was not expected. It shot up like a rocket, and we really could not see that coming at July 1st. I mean, previously we could, of course, take a hint from India and other places, but in the US, it was not happening. When the Delta got here, it totally changed everybody's fall plans. So that's interesting to see in the data that this is such a drastic change. It changed the stage of the pandemic. Now, we can go to a little bit different data and see what was happening when the Delta was already taking hold. Like just a couple of weeks later, already in some countries that had fared really well up to that point, the Delta was starting to happen. So we go to, I don't know, let's say there are a bunch of Nordic countries, let's say Finland, for instance, and see what was happening there. There was just a few days, maybe a week of a peak that was starting to happen. And indeed, the predictions were, and actually we can look at the current maintained predictions that they had at the time, that there was going to be if you don't do anything, there's going to be a huge peak. And of course, they did actually do something. The cases went down. But if you zoom in here, you can see that the peak is starting to rise, and it tracked really well. The predictions were quite accurate. When we saw this, we wouldn't believe it. I mean, it's like, no, that's not so bad. This can't be happening. Something is wrong. No, it actually wasn't. This was an accurate prediction. And they indeed did eventually have a partial shutdown that helped them. And same thing is happening in Australia, and it's still happening. We can go to Australia. Australia, of course, has stayed outside of the pandemic pretty much, which is great. But now they are seeing this kind of a peak starting to rise. And that's very interesting because you can go here, zoom in, you still don't see anything. You really have to zoom in and start to see this rise. And already the models predict that it's not going to be good unless you start dealing with it. And they are doing that. They are starting restrictions very recently so that they are coping with it. Okay, so that's the kind of demo, that's the kind of a interface we developed in order for people to explore not only, of course, the pandemic, but also to understand the prediction and prescription and what you can do with this kind of an approach. We've learned quite a bit already about the pandemic and about the predictions and prescriptions. It's been fascinating that the models have been about 2 weeks ahead of the world in recognizing what's going on. And a lot of times it's been like, we don't believe it, but then a couple of weeks later, indeed in the press and publications, things come out. For instance, the focus on schools and workplaces was a really early one. We said we get these models really early that want to shut down schools and workplaces. And indeed, it turned out that it wasn't so much surfaces. It was when you sit down with other people for 8 hours a day without mask at the time, that's when you spread the disease. And also very recently, these Delta surges were things we didn't believe. They happened in a bunch of countries that did not have that much past with COVID. And that's exactly what's happening now. Also, the counterfactuals are new, but they form a window into pandemic phenomena in general. So we plan on going back and analyzing what interventions really matter. We have anecdotal evidence like UK early on could have avoided a shutdown if they only had shut down schools and had some workplace restrictions like 2 weeks earlier before the shutdown. These are kind of interesting. Of course, it's easy to say now, but if you can discover principles like this, they might be something that can be expressed as rules of thumb and decision makers can take into account. We also found that there are differences between countries. Our models so far don't know about the country. It only knows about the curve. But what we learned from China, South Korea early on did not apply as well to Italy. Italy has different demographics, different culture. They should have fared better than they did early on. And now we are working on, when we have enough data, to form a country signature from the entire pandemic and then apply that as an extra input so that we can be more specific to a particular locale. Now, let's see, how are we doing on time? I very briefly want to point out, hopefully have some time for questions in the end too. What came of that demo? It's still happening, of course, and we are revising and are almost ready to release 2.0 based on data, based on country signatures, also taking vaccination into account. But also early on, we discovered that people were really interested in building these kinds of models, predictive, prescriptive models. And we were contacted by XPRIZE, which is, of course, the nonprofit institution that ran the original challenge for space launches, spacecraft, and many other challenges, mapping the ocean floor, feeding the next billion people. They've done a lot of these challenges, and they actually wanted to do a challenge on pandemic response. And we did do it. We provided the technology, the prescription models, and also evaluations and a software that allowed you to develop them and test them. But the participants could take any approach they wanted. They did not have to use ESP. They didn't have to use evolution. They didn't have to use neural networks. And indeed, people used all kinds of approaches, epidemiological models, reinforcement learning, Bayesian primary optimization, all kinds of things. We started with 100 teams, and those who did well in prediction then did prescriptive models. And in the end, we had two winners, one from Valencia, Spain, and another one from Ljubljana, Slovenia. And they did quite different, used different approaches, and did quite well. And Valencia team also, while the competition was happening, actually was advising the Valencian government about what they should do. And they were able to stave off a peak in early 2021 based partly on their work. So this was really interesting that there was so much interest, so many different approaches, but also that we could build a whole ecosystem of people coming together and coming up with ideas what to do. Taking their ideas, taking their models as raw material for evolution, we could then build even better models. And this is two experiments that we did, starting from the models that people provided, distilling them to neural nets and then evolving the neural nets. We get a really much better Pareto front than the human contributions themselves originally. And also, this is a better Pareto front than when we try to do the initial models by randomly generating them ourselves. So humans have a clue. They have ideas that work. And AI can put them together into something even better. So this is a fascinating opportunity for the future. And in the big picture, in the future, we hope that this approach could be taken out to other pandemics, maybe, hopefully not, but maybe there will be others. We'd be ready. But decision-making in general in society. We can finally have a society we want. We have to decide whether we value productivity, equality, environment, many different objectives perhaps, but then we can give AI the job of finding the actions that get us there, the optimal trade-offs. The decision makers still have to pick the trade-offs, but there's no longer graft or pork or other things that get in the way of implementing those ideas. So this is a big promise, perhaps pie in the sky, but that's how we could really use AI while humans still stay on top of what we want. And we can finally maybe be successful in building a society that that is to our liking. So that's it. That's the conclusion. With the ESP, we utilize a surrogate model as well as customization, and can get solutions that are automatically regularized. In terms of the pandemic, we have a way of creating prescriptions and also making it a tool that decision makers can use. And in this way, hopefully in the future, we can have this creative, trustworthy decision making in various aspects of society. And again, if you're interested, you can go to the website. You find more information about ESP, including some game playing applications and papers and other demos. And of course, take a look at that site for COVID. That should be fun. All right, we still have a couple of minutes for questions. So let's see if there are any.
Risto, we do have one question, and it has to do with predicting outcomes, in particular the nexus between that and human nature, which I think probably COVID-19 was a good example of it, where you had people who, without getting too far into politics, either decided to get vaccinations or not vaccinations, wear a mask or not wear a mask. And even the idea that over time, as the guidance changed from varying governments, people were less willing to follow the guidance. Is there a way, I know you mentioned doing country-specific profiles to put that kind of human nature into the predicted outcomes? And is that just based on getting data over time? And if so, does that mean that we're in a better position to make predictions for a future pandemic?
Yeah, you know, that's really a very, very good question, and something we think about every day. Now, if we have enough data, we don't need to characterize what exactly different groups of people do, because all that data is, all those behaviors are expressed in these curves. And we learn how to modify those curves with the MPIs. The mapping from the MPIs to the curve may be complex and involve many groups and interactions and all, but we don't need to understand it in order to predict, if we have enough data. Now, and it looks like actually in a case of the pandemic, it's there. It's surprisingly good. But on the other hand, we would want to make it more fine-grained. This is at the level of, you know, countries and states. And there's a lot of diversity in local decision-making. Cities have their own ordinances. Schools have their own ordinances. So we would like to get to that level eventually. I think it would be more effective. And then, yes, then it would be more, we don't have that much data from any particular location. So we would like to still use data from other locations. And now it seems like we should have a characterization of how these locations are similar or different. And that is perfectly possible. We can have context variables. We didn't really use that many context variables. It was pretty much just a time series. But now we can have vaccination rates. We can have obesity rates. We can have mobility data. Data that is available can be plugged in here. But it's still a research question of what kind of data is predictive and helps us improve accuracy, instead of making everything look so different that we cannot generalize between them. So there's a sweet spot there. The granularity has to be right compared to the data, but that's a future research. But it is compelling. We absolutely have to go there, do that, at least test these different data sources and combine them and see if they help.
Great. Thank you, Risto. That's all the questions we have for today.
There's one question in the chat that I see, actually.
Oh, somebody.
Have you ever done any?
Yes. Have you ever done any modeling in molecular systems? Interesting.
Yes. As a matter of fact, yes. This is still, again, it's on the drawing board, and we've done some preliminary studies, but there's a great opportunity to design molecules to perform certain functions. So for instance, CRISPR. CRISPR is a technology for editing DNA. It has a guide molecule, RNA, that binds to a certain location. And we've gone as far as modeling the binding strength. So we can predict the binding strength of a given molecule pretty well. Well, the next step would be to design that molecule. If we have such a surrogate model of binding, we could design the molecule that optimizes it so it's more specific. So this is something that we've been talking with various institutions who could provide such data. The challenge still is to have enough of a coverage. Only a few molecules have been used so far, and we would need to have many different kinds of molecules, a diversity, so it would support the search. But there may be other similar applications, and you can absolutely do this. Design molecules. Well, first you have to build a predicate, the prediction model, surrogate model, and then use the evolutionary design to come up with molecules that optimize the function. So this approach is really general, and I think that this will be an application that will come out in the next couple of years because the data is coming out and it's almost ready.
Excellent. Thank you. That sounds like it could be very useful in coming up with new potential materials for manufacturing in particular.
Yeah.
I think that is all of our questions for today.
Okay, and we're right on time. Thank you.